Hey everyone. So today let's look at something interesting. One of my friend who is a staff engineer was recently interviewing at multiple places, and uh, he found something quite interesting during his interview processes. Especially with these lead code style interviews and how they kind of work against senior plus engineers. If you haven't heard about it already, there is a general talk in the industry that senior plus engineers usually find it difficult or challenging to pass these lead code style interviews. Yeah. And there is a specific reason for this, and we'll look into it. So I have modified a question that my friend was asked, and we will look into the specific question and also see why when we optimize for like these competitive programming style solutions, and when we look for that sort of solutions, we would be filtering out people who have had experience with me dealing with ongoing maintenance cycle or building something that scales over time when the requirement changes and things like that. Yeah. Let's look at a practical example and why it might not be the right or a proper way to assess senior and senior plus engineers. Yeah. So let's get started. So uh, let's look into this question. Yeah. So it's something like this. Given a stream of integers, find the product of the last k integers. Assume that k is always less than the size of the stream, uh, and the stream is not empty, and k is always a non-negative integer. The stream is not empty. That doesn't make sense, but it just means that there will always be numbers in the stream, and k is a non-negative integer. This is kind of important. Let's look into that. So what is asked out of this question is write a class that has the following methods. Uh, so first thing is add, that just add the number to the stream. So it just puts it into the stream basically. And then get product, and it accepts a parameter of k. And so what does that do? So it returns the product of the last k integer. So it basically tails it. So the last n uh, product of last n integers in the stream. Yeah. So example is an example is this. So when k is 3, so that's 1, 2, 3. So that's 5 fours are 20, and 20 into 3 60. So that's why we have 60 here. And when it's 2, it's 5 and 4, that's 20. And when it's 4, it's 5, 4, 20, 60, and 60 twice is 120. So that's why we have these numbers, yeah? So this is the question we have. Now let's look into solving it, and let's also see where the problem arises when testing for certain kind of or expecting certain kind of solutions for these kind of made up puzzle problems. Yeah. Let's go. So yeah, so I just wrote a small solution in JavaScript, but it doesn't have to be JavaScript. You could write in any language. It's just yeah, I just wrote it in that. So the like this doesn't necessarily have to be a class. It can be just methods. But since the question asked me specifically to create a class, like a class, so that's why I just wrote a class there. So let's go. And so we have these kind of things, right? So what do we have here? So we are initializing the queue to an empty array when we create a new instance of this class. Uh, and then add, which is supposed to be pushing items into this queue. That just pushes it, normal stuff, nothing fancy. And then this one is our last k. So the slice method, as we can see, it returns a section of an array for both start and end. Yeah, it just clips out the portion of the array. Yeah, so that's what we need to do, right? Like from the last. So from negative k, if we add it as negative k, so it will be from what was inserted last. So it will be more like a stack data structure if we think about it in terms of data structure. Yeah, so it will just pop out the last k, and then what we do is we just multiply it using a reduce method. So first thing is node, right? Yeah. So when I run this, let's see if, yeah. So the products are, so the last three, which is like 5, 4, and 3, 20, 60. So that's fine. And the last two is 20, last four is 120, and the last one is 5. Yeah. So this works as expected, yeah. And the thing is, we are doing this in O of n, like linear complexity. This has a linear complexity. Let's look into why, like, assessing this sort of complexity is basically pointless here, because the thing is we have to reduce the complexity now. So to reduce, which is like in constant time, we have to perform it in constant time. So that's the expectation, right? So if we try to do that, then we will introduce a lot of anti-patterns. Let's look into that. So if we have to do like a constant time product, then what we have to do is basically whenever we insert it, we have to get it as a product. Yeah. So instead of this, we will be doing is, let's say, yeah, this copilot is suggesting some nonsense. We don't have to worry about that. So this will be my last product. But the thing is, if the queue is empty, then we have to consider that, right? So if there is last product, then we just multiply that with the current number which is coming in. Otherwise, we just put in the number. So we just have to push this. We push this into the new product. So now we have to modify the get product to retrieve the product in constant time. So let's get rid of this. And then we divide by the product of everything that's before uh, the k trail. So what do I mean by that is, uh, so our original stream will be this, and our product, like the localized computations we do at each step. So that will be this array. Now, for example, if k is 3, then it's this tail. So that's like 20, 60. So this should yield a value of 60. But how do we do that with our this product array? Uh, so what we have so far, so the max product is product of everything. And if we want the product of the last three, then we have to divide it by whatever is before the last three. So this is our last 3k equal to 3 trailing thing. So whatever is before this is these two. So that's how we get this one. So for example, here k will be like 3 plus 1, that's 4. And 5 minus 4 will be, because the queue length is 5, 5 minus 4 will result in the index of 1. So here, the index of 1 is the value 2. So what would happen here is like 120 divided by 2, and we get 60. So that's how this math works. Constant time, let's this. So we get the same result, right? Yeah, we get 60, 20, 120, and 5. We get the same stuff. Uh, But we will run into some interesting constraints here. Like before even we go into that, there is an obvious thing we are doing here. We are uh, modifying the original sequence, right? So if at all, let's say in a real project, what happens? The requirement kind of changes over time. Not kind of, the requirement changes over time. So now we have it in constant time, but there are a couple of issues here. So uh, let's see from a maintainability point of view, right? We have modified whatever copy we received from the stream. Now we have stored it as product, and uh, that works well if we have to just get the product. But let's say down the line the requirement changes, and we have to also find other things like square root or something like that. Then we have to calculate the original thing back, which is like uh, something like this, which is like a repeated division or something we have to do, and that would be a linear operation. So just by optimizing for this, we have made any future extensibility of this a bit more tricky or less performant compared to this one, because if all we wanted is O of one, like constant time for this operation, then we are doing that at the trade-off of other operations. And over time, this is a bit tricky because now we have lost the original data and we have to recompute that original data. Whereas in the O of n, which is the linear time complexity solution, we always maintained what we got from the stream. Or so, yeah, we had the original data there. So every solution will take a linear time, which is a good trade-off in my uh, perspective, because unless we know that only a specific operation is done more than the others, if only we have that data, only then we could optimize that specific operation at the loss of taking more uh, time complexity in other operations. But at this point, uh, just doing this at uh, constant time doesn't make much sense. That is one issue, but that's kind of a subjective thing, right? So let's skip that part and let's get into the actual code problem that we would run into. So now this will work, but what would happen, let's say if I add add a zero to this. Now this entire solution would break because we don't take zero into account. So now what we have to do is to handle zero, uh, we have to make some special cases. So, but how will this be handled in the O of one? Let's see. Then it works as expected, right? So because how would this be? So this is the one. So get product of three. So last three. Uh, no, this is not the one. So after three, we have like the zero here. Yeah. So the product of last three is zero because we have a zero. That's fine. Product of last two is 20. That's good. And then last four, we have a zero. So it will be zero. And the last one is five. Yeah. It works without any special case handling. Like zero is handled in this or one. We didn't, if you look at it, we didn't have to do anything special for that. But when we go for a constant time complexity solution, then this breaks. And we have to uh, do some special handling for that, which, in my perspective, usually if you have to do anything for a specific case in a code, that's a bad design in general because it signals some sort of a deeper problem in the code itself. Now, what I have to do is now I have to just then have to write something like this. I have to handle this zero specifically now. So this is a very specific condition, and the earlier solution, although the time complexity was like O of n, which is linear, we didn't have to uh, write our code to handle special cases, and we don't have to reset the queue. Uh, yeah. So, but now we need to handle this special case here, which makes it a bit of a not so good code because we have some additional logic to check additional conditional for a case. Like where this comes from is mostly from the idea of clean code, and also if you had listened to Linus Torvalds in one of his interviews, he mentioned something on this. Let me pull that video up. So let's listen to this. I guarantee you, everybody who raised their hand, they have done what's called a single linked list. And it's taught this, the first not very good taste approach is basically how it's taught to be done when you start out coding. And you don't have to understand the code. The most interesting part to me is the last if statement. Um, because what happens in a single linked list for you, this is trying to remove an existing entry from a list. And there's a difference between if it's the first entry or whether it's an entry in the middle. Because if it's the first entry, you have to change the pointer to the first entry. If it's in the middle, you have to change the pointer of a previous entry. So there are two completely different cases, and that's better. And this is better. It does not have the if statement. And it doesn't really matter to you. I mean, I don't want you to understand why it doesn't have the if statement, but I want you to understand that sometimes you can see a problem in a different way and rewrite it so that a special case goes away and becomes the normal case. And that's good code. And yeah, so this is the point I'm trying to make as well. Code, yeah. So this is the point. Like this doesn't need to be a special case. This could have been a general case, like because as we have seen when we do that in a linear time, we handle this stuff zero as a normal case. And now when we um, optimize it for time, we run into this problem of a special case and handling that special case separately, and then resetting the queue which we are doing it, which kind of complicates it unnecessarily and for not that much of a gain, I would say, because all this is doing is like integers. And this is the problem I'm trying to bring forward or like put forward. Uh, like when you are a senior developer, these are the kind of things you would concentrate on, like the maintainability, the long-term maintainability of code, senior or senior plus. These are the sort of things you would put your most of your mind on, like how do you write maintainable code. And here the interview or the solution that is expected out of the interview doesn't really test for a senior engineer's actual job. Like CPUs are cheap, like compute is cheap. Uh, So a linear time is not going to become a problem for most cases. There are some situations where it will become a problem, like if you're writing some embedded system code or memory limited or compute limited code, then probably you will have to optimize for it. But most of the code, if you're writing for web, and if you're going to run on servers that are cloud hosted, then this is not generally a problem that you will run into often. And testing for this and missing the actual point and expecting someone to put in an anti-pattern into their code to pass an interview, I don't know. That kind of uh, l- that kind of feels counterintuitive to me. Like, why are you hiring that person in the first place for a senior plus role or staff role? Uh, yeah, so this is the thing I wanted to talk about. And then it doesn't just end here because now we have done this, uh, our other stuff will break. Yeah, so this will no longer work because now the value of k can be greater than the actual q because of we are resetting it here. Now we have to write some custom logic to check if that is greater than and then handle that. It's all unnecessary complexity, and it just makes the code uh, difficult to maintain than if it was just a linear time thing. Yeah. So there are places where you have to think about these, but for web scale things, I don't think you would mostly run into such level of optimization, micro optimizations. And as you can see, with the advent of these Copilot and all this stuff, does it really even make sense to test on this triviality which a machine completes? Or does it make sense to test senior plus engineers on the actual, how they write actual maintainable code, scalable code, and how do they design stuff in a scalable way? Would that make more sense? Because what are these people who are going to be hired in this position going to do in the organization? Like, yeah, there's a lot to think about here. So yeah, that's just my take on this entire thing. Let's be more pragmatic. Just this lead code stuff, yeah, it makes sense to companies like Google because they get tons of applications a day. They need some sort of filter. But if you're a startup and if you're doing this, then I don't know what you're doing. Yeah. So that's my rant for today. I'll see you later then. Bye.